Hello, this is Danilo. We're doing the Habra High School Chemistry Winter Final Review. Looking at the review and seeing what some of the answers are on the final review. First, we're starting off with how many valence electrons are in an atom of magnesium? Most of us don't have this number on top of our head, so the first thing we do to look at valence electrons is look at the periodic table. For all the represented elements, which are groups 1 through 7, the group number tells us their actual representative. So here's magnesium. It's in group 2 and 3. We could see it's under group 2A. Now the CST has a very similar looking type of periodic table, so we could just use the group number to figure out for magnesium. And the correct answer is A. How many valence electrons are in an atom of magnesium? And the answer is 2. Everyone else in that family, beryllium on down, also has valence electrons of 2. And that's kind of the structure of the periodic table, that everyone that's in the same family is going to have exactly the same number of valence electrons. Now let's go to our next question. How many valence electrons does helium have? Helium doesn't follow this rule, of course, it's the exception. But we all know that the atomic number for helium is 2. We can take a look at helium in terms of electron configuration. Its electron configuration is 1s2. So it has 2 electrons, and they're both in period 1 or that. So the answer to how many valence electrons does helium have is 2. Now let's read number 3. The electrons in the highest occupied energy of an atom are called orbital electrons, valence electrons, anions, or cations. The correct answer, it's one of those 4. The answer is valence electrons. Many students choose A because it sounds something, we talk about orbitals all the time. It sounds familiar, but they prefer to choose something that looks familiar that they don't. The reason why orbital electrons would be the wrong answer is because you have orbital electrons on the inside as well as the outside. So valence electrons is only talking about the highest occupied energy level. Also, it coincides with your periods with the periodic table. Now let's look at both more periodic table questions review. The first one is, how does sodium obey the octet rule when reacting to form compounds? It A, gains electrons. It gives up electrons. It does not change its number of electrons. Or D, calcium does not obey the octet rule. Well, the answer here is that sodium is a metal, and metals have the tendency to give up electrons. All metals give up electrons to form cations. An analogy is that, for students in lunch, if you forgot your lunch and it's 40 minutes away, do you go through all that effort to either call your mom or go walk that 5-mile walk home and get your lunch? The outer orbitals requires a lot of energy for most metals, and they're just too lazy to keep up with all that extra work. It's like most things in life, when you have to do a lot of work for something very little gain, most of us are just not willing to do that. Now we're going back to electron configuration, in particular that of gallium. Now there's different ways to solve it, but the most important thing is actually take a look at gallium on the periodic table. And we see here's gallium. We don't know where it is. It's not something we usually work with that often. It's in group 3, and it's in period 4. Those two things are very important. So let's just see, and this group from everywhere from 3 to 6 is what we look for, the p orbitals. So it's actually only going to have a 4p1. So that's the first thing we want to go back to our answer and see, does anyone have a 4p1? And then we notice that it's D. It has a 4p1. No one else has a 4p1, so that's the answer. There are 2 ways to solve this problem. One is to use the periodic table and look at all the ones that have the filled up d orbitals and choose the one that has that 4p1. The other approach is to see what should be the last valence electron, which is 4p1, and just use the process of elimination, saying these guys just not going to work out. Just don't have the right information. Now we're looking at the periodic table, and we're going to look at the charge for selenium ion and make sure we get the right minus or plus as well. So, where's selenium? It's not here, right? It's actually right here, underneath, part of the oxygen family. Now, most of us don't go around calling people 6, 7, 8, right? It's like calling your friends by their phone numbers. We call things in chemistry, in terms of families, by the first atom. So anyone underneath oxygen is part of the oxygen family. Most of us are pretty familiar with the charge for oxygen. Oxygen has a -2 charge. And the easiest way to do this problem is actually to know that it's part of the oxygen family and the charge is -2. The other way to do this problem is actually to go to the group number, which is 6A, and subtract 8. And you can do that for mostly 5, 6, 7, and nonmetals in particular. And you would get the charge. Being 6 minus 8 would give you that -2 charge. We're going over a more octet rule. The octet rule states that in chemical compounds, atoms tend to either A, look for the electron configuration of a noble gas, B, they have more protons than electrons, C, they have 8 electrons in the principal energy shell, or they have more electrons than protons. So the answer is the octet rule, even though it's not named the right way for most chemistry students, is that the electron configuration of a noble gas. And for most electrons, this is going to be 8. The obviously exception being lithium, beryllium, hydrogen, helium, which only need to have 2 electrons in their outermost shell. Obviously, answer C is kind of the get the students to guess on it, even though it's the wrong answer. Answer D, having more electrons than protons, is specifically referring to anions, which is not really has anything to do with the octet rule right now. And this protons more than electrons is just not the right answers. There are many same name of electrons and protons in all atoms, and we're talking about atoms, not ions here. And this is one of the basic theories of subatomic theory. Just be careful about the octet rule. Just don't always put blindly it's the one with 8. Periodic table. How many electrons does potassium have to give up to obtain noble gift? Now the question is give up, right? That's something students may not be aware of, just that vocabulary. Give up, what does that mean? That means that they're not going to have that electron, in the case of potassium, in its outermost shell. And that is something that being held in the 4th, which is a lot, pretty far. It requires a lot of energy for potassium to maintain that electron out there. So it's in period 4, so it's pretty out there. So the answer is, being in group 1, it's only going to give up 1 valence electron. Now to go beyond that, it's going to require very high ionization energy, so it's not very likely that it'll give up more than that 1 electron. 2, 3, 4, it's not going to want, because it wants to stay in the octet rule and have a completed 3rd shell. Is that, questions may just be guessing answers and not necessarily want to take the time to read the question. The next question in the periodic table is, what is the formula of the ion formed when fluorine achieves a noble gas configuration? Our choices are F +1, +2, -1, -2. Now a lot of students are going to make a mistake on the left and the right, right? So fluorine, which is to the right, and my analogy is, let's just draw a periodic table of the United States of America, right? Here we have Texas, you got Florida, and here's the East Coast. What do we know about people from New York? Are they happy? No, usually they're negative. And everything to the left, remember California, were the land of the happy cows, were positive. So if you're on the right side of the periodic table with all the nonmetals, you're going to be negative. Over here is positive, all that sunshine from California. So that's one way to double check to making sure that you're putting the right minus or plus. Even though you figured out that it's negative, you're going to have to know if it's negative or plus. So fluorine on the periodic table is -1. Which of the following elements does not form an ion with a charge of -1? Now, the important thing is to figure out who does not fit within this group. Fluorine, iodine, and bromine are all halogens. So the only guy that doesn't fit there would be sodium. So it'd be a good guess to guess that sodium, which actually has a +1 charge, does not fit in with the rest of the halogens. So part of test taking is to figure out that these three are in the same group and sodium does not fit in. So obviously that's the answer to choose, which is A, sodium does not. The keyword is not. A lot of students might just be going really fast to the test. They're in a rush to get over. Their mind's not thinking. And they all know that fluorine and iodine are the same group. So if you just look at the first right answer, you're not answering this not type of question, which is difficult for some students. Now we're going back to electron configuration. A lot of us has forgot this is what, 3-4 months ago that it was taught. Now, noble gas, I'm just using a simple analogy that mine is you have to have, for me, the perfect dinner has a 2-liter soda and 6 slices of pizza. So it's 2 liters of Coke and 6 slices of pizza, right? Of soda. And then 6 pieces. So it has to have 6 in the P and 2 in the S, basically, to be a noble gas. This doesn't have, it has a D. That's not, you don't want that. You have 3, that looks pretty good, right? You got the 3S, 3D, that's filled, right? And then you have that, which is the 4S2. So obviously this is wrong. This technically could fit, and that's why it's called a pseudo, there's actually a word for it, a pseudo noble gas configuration. And that happens with people like chromium and silver that actually have a pseudo net. But it's not because the outermost shell has these extra G's there, so it's not right. So the only noble gas would be B, which is argon, which has a 1, 2, 3 completed shells. Next is, how does oxygen obey the octet rule when reacting to form compounds? Does it gain? Does it give up electrons? And my rule is when we look at stuff that's electronegative on the right-hand corner, that it's just, imagine if you're getting paid. If you're supposed to be getting paid $800 a week and you only got paid $600, would you complain and do whatever and follow up, make sure you get paid that extra $200? Of course you would. So that's what oxygen's doing. It was so close to becoming a noble gas or having a complete octet that it wants to gain what it was missing in terms of that 2 electrons that it's missing. Oxygen is 2 electrons from the octet rule, and it really wants to be complete. Which of the following is the electron configuration of the fluorine ion? This is a concept that a lot of students are getting confused on in terms of their first guess is just to write out, oh, fluorine, and I know the electron configuration, they're proud of it, and they're going to put down 1s2, 2s2, 2p5, which is the right one for fluorine, but that's not the right answer for fluorine. That would be B, which is actually fluorine, which it has, what the negative stands for, it has the extra electron. It goes from 2p5 to 2p6. So the answer is B, 2p6. A good guess for most ions is neon, since most commonly used atoms that we use in chemistry class, like carbon, nitrogen, oxygen, all look like neon. Students may not use answer B because they think it has to be written like 1s2, 2s2, you know, where I don't see 2s2, 2p6. So we have to be able to do definitions knowing that neon is actually a noble gas and it fits 2s2, 2p6. Potassium ion looks like argon, but it's obviously very, very huge in terms of a lot bigger than neon. Now we have to look at iodine. Iodine, this is a pretty hard, not in terms of that difficult, but iodine is way down there for the halogens in terms of it's going to have a lot of stuff in there. So here's iodine. It's in 2, 3, 4, 5. It's in 5s. It's going to have a 5s, all that 5 stuff. And it's going to actually look like xenon. It's going to make sure that its 5s2 and 5p6 are all complete. So the correct answer is, with the 5s2s and 5p6 complete, is A. The rest of them don't have, B doesn't have anything in the 5s, C doesn't have complete 5, and D doesn't have anything in the 5s as well. So the answer has to look like xenon, which is 5s2, 5p6, which has to be complete. Number 15. What is the charge on the cation in the ionic compound of sodium sulfide? Wow, this is, I would think, one of the most difficult questions on this assessment in terms of what the heck are they talking about. So there's a lot of vocabulary going on here. First of all, you're talking about ionic compound. Ionic compounds are always neutral, so their charge would be 0, and that's kind of the misleading answer, which is wrong. Because we're not talking about the ionic compound. What are we talking about? We're talking about the cation. So is the cation the sodium or the sulfide? 50-50 guess. Now we have to go back to our drawing of the happy cat, with a big smile, right? And positive. How do we become positive as a cation? We have to have obviously a positive charge. And sodium, when you look at the periodic table, it's group 1. So we know the charge is 1, so that's our right answer. It is a +1 charge. But it took a lot of figuring out in terms of what are we solving for. Are we solving for the cation? Are we solving for sulfide or sodium? Are we solving for the ionic compound? Once we know that, we can figure out, oh yeah, sodium has a +1 charge once we break that down into that. Most of the students, it would be somewhat difficult in terms of figuring out what the question's actually asking for. Number 16, which of the following occurs in ionic bound? Bound, pure definitional. Ionic bound has a lot of stuff going for it. It has definition-wise, it is two opposites that attract, kind of like life in general. Two atoms that share electrons is obviously going to be covalent bonds. Two atoms share more than 2 electrons. That's more sharing, which is more covalent bonds. Like charged ions attract. Ionic bonds are always formed between a cation and anion, which are opposites. One's positive and one's negative, so that would not be the right answer. So the right answer is oppositely charged ions. Ionic bond, here's just the definition, is between a metal or non-metal. The other way to look at it is between a cation and an anion. So students need to be able to go back and forth through the different definitions and terms and know that we're talking still about an ionic compound or ionic element. Number 17. Which of the following is true of ionic compounds? And this is just one where these are all the properties of ionic compound. It's held together by ionic bonds, composed of anions and cations, and the answer is simply all of the above. This is to see if the students know all the properties from definitional. This is as straightforward as you can get in terms of question, in terms of straight out of the textbook. And also, like, if students just don't look at, oh yeah, just jumping at the first answer. Oh, it's held by ionic bonds, so it's the right answer, right? B. They don't look at all the answers, including D, which says all above. So important test technique in heat, before you put any answer down, you make sure that you verify A, B, C, and D to make sure what kind of question is being asked and what kind of responses are there available. Now we're looking at aluminum oxide. Aluminum oxide should obviously be memorized by most students because we work with it so many times, but there's different ways to derive it and figure out if you have the right one. So most students are familiar with this problem with balancing. It's a classical balancing problem. Aluminum gets its charge +3 because it's in group 3, while oxygen is -2 or group 6, so it has a -2 charge. Students that don't want to memorize common atoms should be practicing balancing. There's videos on YouTube where you can get more information on that. And what you do is basically the first step is to make sure, are the charges the same? In this case, they're not. We have an Al +3 and an oxygen -2. So what we're going to do when they don't equal the same, we just cross the number to make it the subset. So we were going to write out Al2O3 by switching the charges down to the opposite. element. Next, what is sodium sulfate? So once again, students need to be familiar with their polyatomics and knowing that sulfate is SO4 with a -2 charge. So they could either memorize that with flashcards, they could use a mnemonic such as Nick the Camel, which they can watch on YouTube as well, or they could use a polyatomic chart, which most high school chemistry teachers are providing their students to reduce text anxiety, and since not everyone is motivated to learn the polyatomics in terms of we really want to measure more the conceptual knowledge, therefore, than the ability to memorize rote memorization. Once again, sodium has a +1 charge, sulfate has a -2 charge, so they don't add up to equal 1. That means we're going to have to do that crisscross. So with polyatomics, when we do the crossing, it's the same thing, but we just treat it as one unit, right? So this has a -2. So that 2 comes down here, and that 1 goes over here. So we cross that here, cross that there. And obviously we're not going to write a 1 subscript, so we just write out Na2SO4 to do the correct balancing of the chemical formula. Now this one revolves a little bit of definitions and knowing the naming of polyatomics and chemical formulas. Which of the following compounds has the formula of CuNO3, which is A, copper 1 nitrate, B, copper 2 nitrate, C, copper nitrate, and D, copper nitrogen oxide. And if the teacher wanted to be a little bit meaner, they could also put copper nitride. So a lot of students get confused between nitrate and nitride. In this, we have copper. Students need to recognize, without being prompted, to recognize what kind of metal is copper. When it comes to proper naming, copper is a transition metal, which means you're always going to include the appropriate Roman numeral. The fact that nitrate has a -1 charge from your polyatomic chart, that means that because there's a 1-to-1 ratio, that means copper has to be, in this particular case, +1. So the right answer is A, copper 1 nitrate. Most students think that NO3 is actually nitride, which is not one of your answers. All transition metals should always have a charge. And it's difficult. This tests students' ability to recognize between different metals, like an alkali, alkaline, or transition metal. But a lot of students are just not prepared in terms of memorizing that. Let's look at 21. Which of the following pairs of elements is most likely to form an ionic compound? So we have barium and fluorine, phosphorus and sulfur, oxygen, chlorine, and sodium and aluminum. Let's just look at these. Sodium and aluminum are both metals. Oxygen and chlorine are both nonmetals. Phosphorus and sulfur are both nonmetals. And the only one that has something different, barium plus fluorine negative, would be barium sulfurfluorine. So the correct answer is barium fluorine. It's a difficult definition type problem question. It's much easier just to say, well, is lithium a metal or non-metal? And it involves students to actually kind of figure out from these 4 choices. This problem requires the students see which of the elements are metals. In this case, only barium and fluorine are the metal and non-metal combination. 22. Which of the following particles are free to drift in metals? This is just a simple sizing problem, right? So my example is if you live in San Francisco, if you have to have some form of transportation, obviously a bicycle or rollerblades is a lot more efficient in terms of parking than having a big car like an Escalade or F-350 or some huge car. So students need to recognize that an electron is about 2,000 times smaller than either a proton, a neutron, or a cation. Cation is just basically a fancy word of saying, ooh, a big atom. And we know atoms are made out of lots of neutrons and protons, so they're going to be a lot bigger than an electron. So the guy that's the smallest is the guy that's going to be able to drift in metals. So the only logical answer would be B. Students can either memorize that's what metallic metals are about, and bonds, or they could just figure out that they're so small that they'll most likely be moving around. What is the basis of a metallic bond? So we can have the attraction of metals to mobile electrons, attraction between neutral metal atoms. That's not it. The neutralization of protons by electrons, which really doesn't have anything to do with just metals. or the attraction of opposite. And that's once again the formula for ionic compound. So the only right answer is for the CO electrons model is the attraction of metal ions to mobile electrons. Mobile electrons have a negative charge, and metal ions, cations, have a positive charge. So there's going to be attraction from a metal ion to all the electrons that are floating around in that metal. So that's the right answer. 24. What characteristic of metals makes them good collectors of electricity? So once again, mobile protons, never heard of that. Mobile cations, they don't move. Crystal structure that can be arranged is not the right answer. So the only answer is the mobile valence electrons, the outermost electrons that are most importantly, right? Uh, 25. Which of these elements exists as diatomic molecules? Is it hydrogen, helium, argon, and potassium? So first of all, potassium usually forms a cation. So someone that forms a cation is very unlikely to make a diatomic molecule, which is about sharing. That's a covalent bond. Hydrogen is a good candidate. And then both neon and argon are obviously monotopics or noble gases. So if we looked at them, they already complete the octet rule, which means they already have their 8 electrons on the outermost shell. So they're not really good candidates to be diatomic. So the only guy on this list is hydrogen, which has 1 electron, but it wants to have 2 electrons. This is a list, a different way of visualizing it for some of us who are more visual learners in terms of just have to know that nitrogen, fluorine, and going down this halogen, these 6 plus hydrogen are or L shape, or the 7. You just do a 7, right? It's a 7, and then using hydrogen, right? 17. That this is how you figure out who the diatomics are. And these are all important molecules. They form important reactions for combustion, or just they're important in nature. So the answer is H, and we already reasoned out why neon and argon, for being noble gases, and potassium, which is a cation, are not the right answers. Let's go to 26. How do atoms achieve noble gas electron configuration in a single covalent bond, which is not necessarily the same as ionic bonds in general? So we're talking about single. It's like having a single pair of shoes when it comes to electrons, because we're actually sharing. So covalent is another word for share. So whenever you see covalent or share, they should be kind of synonymous. So this is 2 pairs share 2 pairs of electrons. So that's like having 2 pairs of shoes. Are we talking about double, or are we talking about single? So we're talking about single. And that's a single pair of shoes, or 2 electrons, or 2 shoes. So that's the only right answer is C. This question, the answers are probably difficult for people who don't like reading word problems, and especially when all the answers, they all look pretty similar. So there's very fine nuance between 1, 2, and 2 pairs. And that fine nuance between the two is actually where the right answer is. So it's this first one is it's a pretty confusing. I don't even know what it means in terms of one atom loses 2 and the other gains 2. So that's kind of more of it's kind of implying it's talking about more of ionics. So for example, magnesium oxide, more so than a covalent bond. That's what we're talking about here. So number 27, how many electrons can occupy a single orbital? And a lot of students are going to put wrong answers. They're going to put number 1. And they're not necessarily using Pauli exclusion principle, which is saying that you can only have, 1 electron. You could have 2, right? But they have to have different types of spins. So the problem is, I think that most students are not really learning the quantum mechanical model of electrons. So in that, you'd go to death in terms of how many different numbers there are. And that's why the answer is 2, and a lot of students are going to put 1. They don't visualize 2 electrons are in the same orbital, and they all have 2 different spins. So one is going different spin, gives it kind of a different charge. So one goes one way, and the other one goes the other way. So one goes clockwise, and the other one goes counterclockwise. So they're going in different spins, which causes kind of a that they don't crash into each other type situation. So, all right, we're talking about Vesper. A lot of students say, "Oh, I don't know Vesper. I'm going to skip this question," but they're really ignoring that they could kind of figure out this question with just the information that's given. Molecules adjust their shape to keep which of the following as far as possible. So, this one is actually the answers are going to give you the solution as opposed to the question, because a lot of us don't really know Vesper or remember it. Pairs of valence electrons, that looks like a good candidate. Inner shell electrons and the electrons close to the nucleus sound kind of the same, and since this is choosing the right answer, these are probably two that we could throw away. So we have a choice between mobile electrons and valence electrons. And we haven't really covered mobile electrons. I mean, yeah, it's for metal bonds per se, but it's for really for molecules. We're always focusing on pairs of valence electrons, which is A. Some students are unfamiliar with Vesper and will panic on this question. It's not necessary to know the details of Vesper, but understand that electrons are like magnets. The same poles, in other words, will repel. Mobile electrons is a fake term, and most chemistry is only concerned with valence electrons. Let's go to 29. What causes hydrogen bonding? Hydrogen bonding is caused by attraction between ions. So we see that we have all these definitions that look familiar from what we've learned in chemistry class, but they're actually describing other types of bonds. A between ions is anything that has ions on it is going to be ionic bond. Motion of electrons, that goes to C of electrons, which is metallic bond. Sharing electrons, sharing is always synonymous with covalent bonds. So they only answered by process of elimination. Bonding of covalent bonded hydrogen ions with unshared electrons is D. It has a small negative charge where the electron pair is, and also a positive charge with the hydrogen. Now we're going back to what we're currently covering, which is stoichiometry. The calculation of quantities of chemical equations called, I always say, stoichiometry. Dimensional analysis is something we learned way back in when we learned significant figures. Percent composition. Percent composition has to do with, percent composition of for example, hydrogen and water. We got to figure out by weight how much hydrogen we have compared to oxygen. It can be a reference to how many molecules. So it's talking about what it's composed of. And percent yield is an equation that we just learned regarding the lab work in terms of what do we actually get in a lab or in a manufacturing situation over the theoretical yield. So that's what we're looking for when we do that. So the answer obviously is stoichiometry. This is a key term in chemical equations, and the other ones just do not apply to that word, chemical equations. Here we get to do an actual example of stoichiometry. So if we have 1 egg and 1/3 of cup are needed, we need to figure out how many cups we have, right? And if we just did 1 bag, 1 brownie, 3 eggs, which means we need 3 brownies, would be the right answer, which is C. And this is how we do the work. Show your work, you got to write the given. The given is the 3 eggs and 1 cup of oil. The wanted is question mark, how many bags of brownie mix? The known is 1 bag of brownie to 1 egg, which is the ratio, or 1/3 cup of oil to 1 bag of brownie. Obviously, we don't really want to work with fractions if we don't have to, so let's stick to the eggs. 3 eggs times 1 bag of brownie over 1 egg gives us 3 bags of brownies. We can do the same thing with the oil. We'll find out that they're both will give the same answer, but basically we want to make the math as easy as we can. Let's go to 32. In every chemical reaction, there's a lot of good answers here. They all look good, but it's kind of hard. I guess there's 2 concepts looking at in terms of mass and molecules are conserved. The reason why molecules are not conserved because sometimes we do a reaction such as H2 plus O2 gives us
H2O. The number of moles on one side is not going to be the same number of molecules on the other side, just because there's different coefficients in the way that we're sometimes combining two molecules to make a new one, or it's called synthesis. So that's not going to be true. The molecules part is wrong, so that means A and D are wrong. We know mass is going to be conserved all the time, so A and C look like good answers, but we just took out that. So now we got to look at liters, right? So liters is kind of tricky because there are reactions where in H2O or making ammonia that it is conserved, but there are situations where we're dealing with liquids and solids, and we're not really dealing with conservation of liters. So that's why this is it's kind of a half right answer, but it's not the correct answer. So the correct answer is C. That massive atoms are conserved. Mass is always conserved, and what we do for the most part when we balance reactions is we're always counting the number of atoms on one side, on the left, and making sure it's the same as the right. So we want to make sure that we have, for example, for the water combustion reaction we have, or for the water synthesis reaction, we have 4H on this side, and we have 4H on here, and we have 2 oxygen over here, and 2 oxygen on the right side, even though they're involved in different molecules. The important thing is that the number of atoms on both sides add up to 4H, 4H, 2 oxygens, 2 oxygens. All right, let's go to 33. In chemical reaction, the mass of products is, it's always equal to the mass of the reactants. And I think a lot of people are putting A because they think this is a reference to a lab situation. And we're not really talking about lab work. This is all theoretical questions that we're presenting to you. So the correct answer is C, which is talking about just the theoretical side of the law of conservation of mass. Obviously, the law of conservation of mass does not work when you have, for example, I cook with my 4-year-old daughter, and she likes to spill stuff all over the floor. So the conservation of mass does not work for the same reasons in a real lab, because there's always error, user error, and also some reactions just don't go to completion. Maybe the situation is not optimal. There's a lot of reasons to that, which is the real world. But when we're doing equations and solving them, on the whiteboard or on the classroom or on an assessment, it's always talking about more of the theoretical side. Let's look at 34. It's also a very tricky definitional type of question. It's trying to figure out, do you know what's really being balanced? So obviously we have 11 and 9 of something. This reaction's always talking, for the most part, when we do our ratios, is always talking about moles. So we have 9 reactants, which is the stuff on the left side, and we have products, which is to the right. The 9 grams of reactants, this is completely wrong, right? Grams to grams, we don't convert directly from grams to grams. So when we do stoichiometry, we always have to first to go through the molar map, going first to moles before we can balance our equation. So B is a very wrong answer. C is liters, which sometimes could work, but sometimes we have, in this case, was actually gas. I didn't write these down. It was gas, and this was actually a solid. So they don't work out because sometimes you have to deal with solids and liquids and aqueous solutions. So liters does not work in most of the cases. And then atoms, obviously, we're not dealing with atoms. These guys are called molecules, so we're just dealing with different concepts. So there's not really 9 atoms, so I'm not sure what that answer is about. So the correct answer is 9. 9 moles of reactants chemically react with 11 moles of product. So here's some quick definition that's going to be on your final assessment, and these are going to be more on your typical matching format, but this is more open response to so that you could practice it. If you don't know these off the top of your head, or you don't know it by reviewing it a couple times, either going through this PowerPoint or this YouTube, what you should basically do is just figure it out, right? So this is mass and or atoms of each element. 48. Reactant that is determined in the amount of product formed is the answer is the limiting reagent. 49. The reactant that is not completely used up in a reaction is called the excess. So it's like when you have excess luggage, or if you have too much cookie dough or cake mix, you call it the excess, right? It's also medical terminology where you remove the excess from the person. 50. The ratio of actual yield to the theoretical yield is percent yield, because we always look at it as a percentage. And if all the reactant is mixed, the maximum amount of product formed is the theoretical yield. A lot of students would put down the actual yield, so this is one thing to be careful. When you see that the maximum amount of product, we're always referring to theoretical being the optimal. So it's the theoretical yield. That is the maximum amount of yield. 52 and 53 are talking once again about single and double covalent. One is talking about single pair of electrons, and the other one's talking about a double pair of electrons. 54 is just talking about the definition of a hydrogen bond. It's a bond between a hydrogen and an unshared, and this is an example of what's going on. Here's oxygen that has its unshared pairs over here and here, combining with hydrogen, and they both have a very, very small dipoles. And 55. And bond is found between atoms of significantly different electricities. And this is once again testing you for your knowledge of ionic bonds in terms of made out of metals and non-metals. Another way of saying that is that they have very different electronegativities. I think we're done.